I think maybe we can get started.
Yeah.
There's a fair amount of people, both in person and online. On mute.
Yeah.
Okay.
Otherwise, I will have to leave in a bit, but I'll catch you at lunch. You're here for lunch, right?
Yes.
Okay, perfect.
Cool.
Thank you all for coming either in person or over Google Meet. It is my pleasure to have Rachel coming here to present her latest work. Rachel is a PhD student at MIT working with Dylan. Before her PhD, she got her bachelor degree from Brock University, double major in both computer science and music. She has very broad research interests. And actually, every time I talk with her, she always told me some new topics she has been working on. I think in the past, she worked on both NLP, computer visions, and robotics. And more specifically, she's interested in AI agent robot alignment to human preference in open-ended settings, collaborative teamings and interactions between human and AI agents, and also decision-making under uncertainty. She was a summer intern last year at the MIT IBM Bosnia lab. She's also a summer intern at the MIT IBM Bosnia lab this year. So she's always a friend of us. Today, she's going to talk about, again, her latest work, which is entitled Flexible Agent Alignment with Goal Inference from Open-Ended Dialog. Yeah, I'm really excited about her talk today, and I guess I'm not going to spend much time. And without further ado, please take it away.
Cool. Hi everyone. I hope everyone online can hear me well. Cool. I'm gonna assume that's a yes. But hi, I'm Rachel. I'm a third year PhD going to my fourth. But I'm pretending I'm still a third year until September hits. PhD with Dylan Hatfield-Bunnell under the Algorithmic Alignment Group. And so yeah, I'll be talking about this work. Various versions of this work have appeared at different workshops at various conferences. So just some disclaimers. I'm going to be using agent and robot interchangeably. So if I in the middle start switching, they're basically the same thing for this talk. And yeah, I'll be focusing on looking at goal inference from human preferences, complex open-ended preferences, and basically how to get agents to better align with those preferences. And this is work done with Dylan, also Andrea Bogu, another prof at MIT, and with some help from an undergrad facility. Cool. So for this talk, we are focusing on agents, such as LLM chatbots or robots, assisting humans in open-ended tasks. And so for the sake of this presentation, I'm going to have this ongoing running example of, let's say you have some sort of agent that asks questions towards a human and can take also actions. And there's a human that responds to these questions according to some preference set that they hold. And this kind of repeats until the ultimate action or your preferences are accomplished. And so kind of to motivate with an example, let's say you have this super complex preference set over you want to bake a cake. And there's a lot of text on the slide, but let's say the things in bold, you want to build a cake or you want to bake a cake. You're not allergic to things. You like unusual flavors, and there's a whole flavor profile that you might have. So you can see here that these are complicated preferences that you might have. And this whole work was kind of motivated by this produced cart from let's say GPT 4.1 mini, which is when I started this project about a year ago. And you can see it outputs a cart, and this is over interaction. So it outputs this final cart, and you can see yeah, it has some of the unusual flavors that you might be requesting for, but then you actually realize that it has none of the actual ingredients to actually bake the legitimate cake. Like, you don't have any milk, you don't have any flour. It kind of like hyper fixates itself on like certain things that you mentioned throughout your conversation, for example. So we can see here that it's not fully aligned. There's some attempts towards what you want, but it doesn't have what you want. And so there's also other prior work done in this field that these are hard for LLMs. So there's a work here, LLMs get lost in multi-turn conversation, and they have this direct quote in their paper that says, LLMs make assumptions in early turns and prematurely attempt to generate final solutions on which they overly rely. And there's also some other work in coding agents that says agents also often hold incorrect expectations about plans from other people or observations in communication. And so in our work, we actually say that we attribute this to, these are probably problems that occur from agents not reliably tracking uncertainty about what the human actually wants. There is a whole subtopic called assistance games that look at specifically, inferring human intent and preferences, but there are some assumptions that are made in these works here, which is one, they assume that the human has some fixed goal in their interaction, and that persists throughout the entire conversation or interaction that you have. And then the second thing is that there are some like predefined set of options that you're dealing with initially. And these assumptions don't actually hold true for most of the interactions we have in the real world. Humans, we change our preferences, we might shift. And the other thing is also like, if we want general agents so that we're not like specifically hyper designed to be like just for, getting ingredients for just cakes, like we also care about coding agents or other things. So there's a lot of options that you can't really pre-design or anticipate to account for. And there's also a lot of cog sci work out there that says like really human preferences are complicated. We don't usually have like come into an interaction with like, this is exactly what I want. There's some work here that shows that really like your preferences are formulated over time, and they also formulate based on like preference elicitation, or if other people ask you questions, then your preferences might like actually shift or get more specific over time. And so here's an example of like going back to, if you want a cake, and if you want like a strawberry flavored cake. And so let's say like you have some notion of goals, starting with like, you might before this round of conversation, you might have thought you wanted like croissants or something, and these other options here. But really, after learning that, hey, you want a strawberry flavored cake, your preferences should really get rid of croissants, because you don't want croissants. And so in this work, we formulate theoretically a type of problem called open universe assistance games that deals with like evolving preferences and complex preferences. We propose a method called Good, which puts this into practice with LLMs for goal tracking in natural language and ranking these goals. And then finally, I'll show like some experimental results and experimental design on how we show that goal tracking is beneficial. Cool. So yeah, I'm gonna go through some theoretical. I don't know how familiar people are with like RL frameworks and stuff, so I'll build through with an example, just to keep things like not too complicated.
I think people are extremely familiar with that. So yeah.
Okay, cool. So yeah, going back, we have basically this robot or this agent that asks a question, or action, and you respond to these questions, and you kind of do that until your task is accomplished. So I don't know how familiar people are with POMTPs. I hope you are, but so yeah, POMTPs are a normal formulation that people naturally use. And so these are types of problems where you assume that you have this agent that goes around and kind of plays with things in your environment, and you get some sort of reward or some sort of change in your environment. And so to go back to our example, and so these partially observed Markov decision processes are often represented by the 6 or 7 tuple. And so in our grocery shopping case, for example, like the state here would be For example, like what's in your grocery cart by the agent, and also like the state of whether like an object is like in your grocery like inventory or not. The possible actions that you can take here, for example, for your agent is like you can take things away from your cart, you can add things to your cart, you can search up your inventory. Your observations would of course be like you can see what's being put in the cart and kind of like the return of your search inventory results. Your reward here would be like kind of like some notion of like how well does the cart match like what you want. And the solution will rely on some belief state, which is like tracking your distribution over like whether an item is in stock. But there's a problem here in regular POMDPs is that they assume that you have some sort of like prefix notion of like what the possible states are. And that's not usually true for purposes like for reasons that I mentioned before. And so there's an existing framework out there that is called Open Universe POMDPs, and they take it one step further, where you can see like the state tuple is now like there's a theta in the state tuple, where theta is kind of like you can have like an unknown number of objects of like unknown type. And so here, the few differences here are like now you also want to keep like an additional like in your state like an additional notion of like some description of your items and if those items are in stock. There's also, oh, that's a little hard to see, but like your belief state is updated to show like also how many items are in this inventory and whether all those items are in stock. But the problem here is we're all different people. We all have very personalized preferences. And so going back to assistance games, this provides like a more natural framework for thinking about these problems. And so here you can see that there's some human, there's some agent or robot that's trying to infer your preferences. The preferences only the human has observations over, like only the human knows what the preferences are, the robot does not. And so basically here you can see that both the human and the robot now can take actions. And so there are some changes here further, for example. So now your state also needs to take into some consideration of like some preference type structure. And for the sake of this paper, we say this preference structure is called goals. And we represent goals in natural language. So they're just like natural language strings that are a couple words long. There's additional actions now you can take. You can actually have a conversation with humans. So now additional actions could be like, oh, the agent will ask a question and you will respond. Your reward has now also changed to like some preference match notion. And your belief state is now really like some belief distribution over possible goals. In this case, like the grocery case, it's possible carts that you can have. And then finally, there's one more step that this doesn't account for, and this is like we have evolving goals that change over time. Like for example, like this might happen when like, you know, if I want rainbow sprinkles, but they don't exist in your inventory. So really like you might want to shift to like, I don't know, pink sprinkles or some other. And so basically what we end up doing is we combine POMDPs, Open Universe POMDPs with, we combine POMDPs with the notion of assistance games. And so now we can get something called Open Universe Assistance Games, where now you have theta, which is like some evolving preference set over time. And both the agent and the human will be interacting with each other to basically find what this preference is. And so here's an example of, hey, your human has like some internal latent state of like in your thoughts, like you have this super long paragraph of things that you might want. And here in this case, it's like you have a daughter who's turning like some years old, and then you want like a bunch of like cakes and balloons and stuff. What you say at each round is like just a direct observation of basically what you have in your head. And your agent should really, to solve these problems, like basically maintain some sort of belief about what the human wants over time. So each round of conversation, it'll have like this like little finite list of like little strings about what it thinks the human might want. And then you can actually like kind of do uncertainty tracking over this list. Cool. And so yeah, so this is a pretty brief summary slide of all the math, but here on the left you have all the POMDP structures, and that kind of takes care of your like state uncertainty. On the right you have Searle and assistance games, which is keeping track of like your task uncertainty over like human practices. Cool. I ran through a bunch of theory really quick. I don't know if anyone has any questions. Cool. And I know Akash was mentioning rewards a lot earlier, and one side note to think about here, I'll talk about this a bit more later, is we don't really have a notion of like a reward function in this case, because things are open-ended and preferences are complicated. So it's hard to actually define a general reward function that fits for everything. So I'll talk about a little bit more about evaluation, about how we deal with that. Great. And so now moving on to good. So now we just talked about all the theoretical formulation of how theoretically how we frame this problem, but now how do we like operate like put this into operation. So we break our system into three main parts. So we have an action module, we have a goal set management module, and we have a goal set ranking module. And so walking through these step by step. So let's start with goal set management. And so at some given time, you'll have some goal set. Of course, at the very beginning of your interaction, this goal set is like empty. And so yeah, at every single round of action or conversation that you do, there is a LLM that is responsible with a prompt of like, hey, given the previous or given your transcript so far in this interaction, and given like your current state of goals, what are good like possible goal sets that should be added, and also what are good possible sets that should be removed. So this is just like a simple LLM prompt. So yeah, for example, like if you determine you want cakes, then like croissants should be removed. And now the good thing about having like a finite goal set management that is dynamic and changes, but is also finite. So there's a good thing which comes from this, is now you can actually break these goals. And so there are a couple of ways that you can rank these goals, and the simplest way you can do is like you can just get an LLM prompt and be like, hey, given all these goals and given the state of your conversation so far, like what is the most likely goal? But we can also do something a little bit more complicated. So you can come up with an actual probability distribution. And so one way that we do is we know that from prior work, LLMs are really good at these binary pairwise comparisons. So what we can do is, hey, just like formulate, like basically sample like different pairs of goals and ask the question like, hey, given your conversation history, which is more likely, like goal set A or goal set B? And basically, if you sample this enough, you can kind of come up with like some success table, like wins and loss table for all your goals. And so now what you can do is basically you can model everything with like a beta distribution for each goal set. And you can say like, hey, alpha for the, like you can estimate the parameters, basically with the numbers from these win and loss scores. And basically all of your goal sets now has like a beta distribution associated with it. And yeah, you can get a probability distribution from this.
This is the aggregate over tokens.
Sorry?
The probability, the likelihood.
So there's no tokens. I can talk about this later. We also do, there was a prior version of this work that we did look at logits, for example. But for now, we're basically like outsourcing to like, hey, given these two goal sets, like which one's more likely? And we like sample various pairs. And so we can like basically come up with a whole success table for like all the pairs that you've sampled.
No, sorry, what I meant by so how are you getting the probability for the in the second part, right? Where you
Yes.
you're ranking them by their likelihood.
Yeah.
Is that right?
Or not by the likelihood, just like based on the beta distribution.
Okay.
Yeah. So basically, like, you can think of it as like another layer of observations where you outsource to another LLM and be like, hey, given what you've seen in this conversation history, like which one's more likely? So it's like another another layer of observations beyond like just the human response.
And how many samples are needed to do
Yeah.
the reliable?
Yeah, that's a good question. So we didn't dig too deep into this. For now, I just said like I believe like we said like 30%. But this is something that is easily changeable. It's just a variable, so you can kind of like increase the number of samples you do. That is a good question though. The reason why we don't have to sample like probably all of them is like because of we didn't dig too deep into this, but like a lot of the goals are actually quite similar. And so basically if you sample like about 30 or 40% of the goals, like that's already like a good enough like enough information to basically solve the task.
So can you help me understand this probabilistic ranking?
Yes.
This is better. How
Yes.
are you building the beta distribution? That only I've
Yeah, so the beta distribution is there's alpha and beta, there's two parameters. And so alpha is basically the win score.
Yeah.
So if you ask like, I don't know, X queries, and then if it like wins like X of these binary comparisons, then you just add 1 to that, and that's like alpha. And a beta is like how many times you lose the comparisons. And this is like you can think of these as like global variables. So it's tracked like for each goal, like for the whole entire interaction. Does that make more sense?
I guess that part makes sense.
Okay.
I'm trying to understand because you said this is a different level of observation that you have. So I'm
Yes.
just trying to understand like mechanistically what are the steps.
Yeah. So basically there's one layer of observation,
Yeah.
which is what the human is directly saying.
Yeah.
But right now we're outsourcing, we want the agent to maintain a belief of what it thinks that the human wants.
Yes.
So we have another LLM layer that's like, hey, I see what the human has responded. I see what like goals I have. Given what the human has said, like which goal is more likely? So this is just like another layer of like the agent looking at the whole entire interaction and being like, this is more likely than this.
Okay.
And not only relying on like we're not
So you're basically taking its sort of binary
Yes.
classification output and then building the beta distribution
Yes.
from it. So kind of beta Bernoulli type setup.
Yeah,
here?
yeah,
Okay.
exactly.
Okay.
Is it like update per step?
Yeah.
And like it's a B score like accumulative over the entire interaction. What's always.
It's accumulated over the entire interaction. There's also a notion of there's four possible outcomes. So either they're both equally likely, or they're both equally unlikely, or one is like much more likely than the other. So we actually do split into 4. So it's not necessarily just a binary, but you can also think of it as like 2 binary comparisons like laid on top of each other.
Yeah.
Because it is important to know like if they're both equally likely or
And how so the language model is verbalizing its output or you're looking at the likelihood?
the language output is just like returning binary. It's like it's greater and slower. So it's actually like outputting something. No, we're not looking at the tokens.
What exactly is that outputting then? Probability?
So it's just like 1 or 0. Like if
But is that a token or is that so okay, here's my
Yeah.
right. So like one way to do this is to say, let me just look at the the cumulative token likelihood
Mhm.
normalized by the marginal.
yeah, so we did that before. I can talk about this later.
Right.
But we did do that method before.
So here, when you say you're not using tokens, what is coming out of the language model then?
Like it's outputting a token.
So it is this is
Yes, yeah. But it's not like we're not looking at the logics. Like we're not
No,
looking at
that's
the
totally fine. I'm just
Okay.
trying to understand this is actually it. So when you say it's probabilistic,
yes.
it's not probabilistic in the sense that you're not using the language model's likelihood.
No.
You're building a distribution on top of
Yes.
what the token comes out.
Yes.
How do you know it's calibrated?
Well, I have additional
Okay,
experiments.
I'll
on this,
stop
so
and work on mine.
I'll talk about that later. There is those are good questions. I do have experiments on those.
And one more final
Yes.
question. So,
My intern.
so when you build the probability distribution, you can sample question like pair comparison
Yes.
from the like goal set.
Mhm.
Is it like a uniform sampling approach or you have like something smarter? like for example, for two pairs that has the like roughly the same likelihood to be preferred, like you sample them more often to distinguish them.
We just do a random sample, random uniform sample. Cool. Great. So yeah, now that we have this distribution, so moving on to the action module. So now we have this distribution, we can set thresholds. So we can set like a likelihood threshold. So only if the likelihood is high enough, then you should go take the action that satisfies that goal. If it's not high enough, then that means that there's something still uncertain, something still unlikely that you shouldn't take that goal. So we set actually two thresholds. So one is the likelihood threshold, and you can get that by taking the mean of the beta distribution for the goal set. You can also get the variance of the goal set and have that kind of be a proxy of like how uncertain you are in that goal. So we set two thresholds. So one is the likelihood threshold, which is like, oh, if it exceeds like 90%, then that means the goal is sufficiently likely, you should go and take it. We also set a variance threshold. Like if the variance is way too high, then you don't want to take that goal because that means like you're not certain enough. So if it doesn't surpass those thresholds, what it really should do is just like on default, like continue dialogue until you get some goal that is like passes these thresholds so you can take actions on. And so yeah, there's obviously a number of different types of actions you can have. And so the default actions that we have kind of like no matter what the domain is we have a continue dialogue action. We also have a confirm preference action. So that's like before the last step of ending task, like you should double check with the human that like all your preferences are set. There's also obviously an end task like action. And then beyond those, there are other like domain specific tasks that I can talk about later in implementation details. And one also important thing to cover is kind of like, oh, you might ask like, how are we exactly building these conversations or this dialogue action? And so for the sake of our experiments, we actually play around with synthetic conversations. We don't actually like humans are too expensive. So like for the sake of like reproducing stuff, we rely on synthetic conversations. And so one thing we do is basically we come up with dialogue, like some dialogue topic to have the conversation on. And so this dialogue topic generation is basically just another LLM call that's, hey, given the conversation transcripts, given what actions are done already, and given like your distribution information about your goals and your current set of environment, like what is the next good topic to have this conversation around? So the important thing here is really it's dependent on like what your distribution, like what your goal set is. And then yeah, we have like separate LLM calls of like to this agent. We tell it to, hey, generate this query based on some description of your agent task, your current transcript so far, your current state of your environment, and of course this dialogue topic. And then you also want to generate a human utterance, and this is actually based on there's a user profile, and so these are different profiles that we construct that have like various preferences, and they're all like similar to what you saw in like my first or second slide of like they're super complicated, and some of them are quite vague, and we had to deliberately design them this way so that they don't just like immediately just like output everything that it wants in one go, and then your agent just does it verbatim and it's done. And this human utterance preference also like again also takes in like the completed action list, the current state of your environment, your topic, and like there might be completion conditions of like, hey, like if you think the preferences are all met, then like output this sentence just so we know that it will stop. Otherwise it'll kind of just keep on going. And so yeah, this is kind of like a big mash summary slide of like we have an action module that is dependent on what you get from the goal set management set and the goal set ranking set. Cool. Are there any questions?
I have a quick question. So here for your to go back to the beta distribution. So if you think you're comparing two goals,
Yes.
so how can you convert that into the eventual distributions over the entire the space of your goals?
Yeah. So as we mentioned, as we see here, like we basically just sample different pairs. And we're able to basically just like the win scores will inform the alpha and the loss scores will inform the beta. And then we just take the beta distribution as a representation of the distribution.
But that's the
And and because like the parameters are accumulated over all the interactions, so we just kind of like assume that that's like over all the goals.
So okay, maybe I got it. I understand it the wrong way, but my thought was, you have two goals, and that comparison gives you one beta distribution.
Yes.
So when you have the third goal, you compare that with the first two.
No, so what we do is we basically just like independently sample pairs, and we ask the same question to all the pairs.
Okay.
And then how many of those they win of all the comparisons, then that gets like that's put into your alpha and beta.
Oh,
So it's across like all the questions that you ask.
I see.
And so basically like during the whole entire interaction, it's like a global variable. So you like accumulate all of the comparisons, it's one like over the entire course of your
I
interaction.
see. And that's why you need to use uniform sampling.
Yes.
Okay.
Yeah.
Got it.
Yeah, I got a quick question. Previously, I was doing some work related to uncertainty estimation in large language model, and recently I have work focusing on the multi-entity system, the uncertainty estimation of the multi-entity system. So basically, previously for the uncertainty in large language model, there have many different approaches, but one of them is semantic entropy. Like you sample multiple times and you do the clustering using some actual model. And when I was doing the multi-entity system and for the uncertainty, I just noticed one problem is the cost. Like you have like in the agent system or the multi-agent system, like for this world, I think we will have a long concern history.
Yes.
And especially in agent system, maybe we need some very powerful frontier closest model. So I'm thinking about the cost of this method. Like in my work, I just give up the method to sampling multiple times. So I just directly use low likelihood. Yeah. So I use low likelihood to model the belief updates in the conversation.
Yes.
So yeah, I'm curious about the cost in this.
Yes. So actually in like 10 slides, I do have the cost metric. So I will, but yeah, you are right. So because of all this extra, like, you can think about this really as like a multi-agent LLM system, right? Because everything is just like, they all have different contexts and they all have their own different jobs. So yeah, so that is exactly true. So our costs are a bit higher.
Okay.
Yeah.
Sorry, I'm still stuck on that. So the beta distribution makes sense in the following way, right? I'm relatively older than you. So typically a good choice for understanding uncertainty or binary choices is to use something like a beta Bernoulli process. Are you familiar with that?
Yes.
Okay, so in a beta Bernoulli process, your posterior will come out to be a beta distribution,
Yes.
right? Is that what you're trying to do here?
Yes.
Okay.
Basically. Yeah.
Okay, so you're making binary choices. That is described by some. Okay, so my confusion comes from the fact that where is the likelihood function there? Because you need a Bernoulli somewhere, but you're using the token output of 0, 1
Yes.
as an approximation to it,
Yes.
which you can make very precise if you just use the likelihood.
Yes.
And you said you have done this before.
We have done likelihoods.
Did that not work?
It did not work as well. I'll talk about this in like one slide. It's literally like the next slide.
Okay.
Yeah.
Okay.
All right. Cool.
I'm very glad that you actually know about these things because a lot of people and I talk to don't.
Cool. Before I move on, does anyone have any other questions about the method?
Can I go back to the?
Yes.
Sorry. So, are the goal descriptions, are they fixed or do they evolve with like as the conversation unfolds?
Yes, so basically, yeah, you have like this global variable G that is initially like empty. And as time goes on, you can remove goals or you can add goals or you can change goals.
Okay,
Yeah.
so like for instance, how would it affect the distribution? Let's say if it's like a Princess Thetan case, what for like?
So basically, another thing I forgot to mention is like for the sake of this, this whole experiment, just to speed it up, like these are like goal sets of sets. Like you can think of these as like goal sets of sets.
Okay,
But to speed stuff up, we just pretend like we're dealing with like we're reasoning about pairs of goal sets.
okay,
Just to like make the binary comparisons faster. Otherwise, you have to ask about like each individual.
exactly.
But yeah, if it changes, we just like in this case, like if like I don't know, Princess Theme, 6 kids, vanilla flavor sprinkles, and then you add like one little like extra substring, it becomes a new goal. Yeah. And so basically, we start a new variable, we track new alpha and beta parameters for that new goal.
But will that cause bias? Because like, say if you have a goal that has a like very high likelihood,
Mhm.
in previous round,
Yes.
and then you add a new goal that is like exactly the substitute for that.
Yeah.
But because it has a like relatively short history, so it also has a short say win score.
Yes.
And the beta like distribution for the win rate will be much smaller
Yes.
than the first one.
Yes.
But the user actually prefer the second one.
Yes.
So will that cause trouble for this framework?
Yeah, so there's a couple things there that might address it. So one is like the threshold. So we set, depending on the domain, obviously, you can set the threshold, and that's kind of like a representation of kind of your like risk threshold of like how much you're willing to be okay with like error, for example, or risk. So we set it like high enough so that it requires like at least like 2 or 3 rounds of you like confirming something before it actually is like taken. So it's not like one round, it's like, oh, something new is introduced and you're like, oh, I can't. Like it takes like a couple rounds to like certify that. I don't know if that answers like part of the question. Okay.
By the way, I like your other part of like using, because now the setup is the following. I think it does make a lot of sense to use the beta as the uncertainty measure.
Yes.
But you still need to understand how you make that missing link of likelihood. How do you replace likelihood with
Yes.
that will be done.
Okay. Yes. So yeah, we're moving on to that topic. So yeah, I've done basically a couple of experiments. And I'll also talk about the logics too. I don't think they're in these experiments, but I've done them in the past, so I'll talk about it a little bit more. So yeah, we conduct isolated ranking experiments, like without the rest of the pipeline, just to like sanity check like how well these methods do. And so basically what we do is we get some common like multiple choice question like data set out there. And obviously like they'll have the question and then they'll have like some number of options. So one thing we do is like we generate like rephrasings of these options and we kind of pretend that for the sake of the experiments, like they're basically the equivalent of our various goals. And we apply like various inference methods on this. And we try like a second method too of like, hey, we just have the questions. We don't take the options that it gives us. And then we basically like have an LLM like generate a bunch of options and then like apply the inference method. And the reason why we separate these out is like in the first case, you kind of are guaranteed that the true answer is in there somewhere. And then versus like this is kind of like closer to like open-ended scenarios where like you might not know what the actual like true option is, and we're kind of like it's just like a closer proxy for what we're doing. And so we basically say check both. Cool. And all right, I'm gonna go through all the methods that we try. So binary pairwise distribution, that's like our method of like with the beta distribution and doing all these binary pairwise comparisons. Prompt likely is just like the LLM prompt that is, hey, like given this question, like which is the correct answer. Prompt directly distribution is give me the like output the distribution numbers. Like given like we give an LLM prompt, it's like hey, here are the options, give me which one's more likely, and also give me all the just like output like a distribution number for each of these options. And then we have like, I'll talk about this a little bit more later, but we have two baselines that we compare against, and that's just like outsourcing to an LLM, like, hey, what's the correct answer?
Sorry, so here you're not looking at the likelihoods directly.
No, so I'll talk about that in a second, because I do have that in, I can talk about, yeah, I do have that in a separate set of experiments from a different paper, but I can talk about that. But, so yeah, one is, you can see for the first like variation of this experiment, our method gets like practically perfect. This is only out of 30 questions, you can do more, but out of the 30 questions we tested, we do amazing. And then the other like methods are kind of comparable. So assuming that the true goal is somewhere in your rephrasings, our method is able to get like 100%. Now, if the options are absent, so there might be cases where like basically, you know, incorrect options are generated as well. So yeah, outsourcing to an LLM to generate the options, they actually all kind of do it comparable. So that's kind of an interesting finding that we had, but we can say at least with the binary, like at least with the distribution methods, you get like a more interpretable number. Like actually, you can get like an actual distribution out, and it's not just like black box. Like, hey, this is the most likely.
But in this case, wouldn't you look at the uncertainty measure more?
Yeah, we could. But
But I mean,
I mean, like here basically what we do is we basically just take the argmax.
no,
And
but I mean, is there data available to understand exactly what happened?
it is not. We have it.
Yeah.
It is not in these experiments, and like we have basically how we test the accuracy is like we take the argmax, like whatever has the highest likelihood, and we just compare it with like the true answer from the data set, and we see if like they're a match. I mean, you could look at the distributions, but it's like you don't really have like an accuracy number to like wisely compare against.
That's fine, right? But I mean, like, if the answer is, since the accuracy is fairly low, a good system, a good Bayesian system would give you a very high uncertainty as well, right? Because or somewhere around,
Yes,
right?
that's true.
Yeah.
Yeah, we have not looked directly into the uncertainty numbers for these. Yeah. So yeah, on a tangent, because I know I promised like talking about the logins, but we haven't gone on there. But I do have another work where we like a very early version of this work where we did look at using the logins. And so what we did there is we had a specific inference prompt that we use, which is like it basically feeds in the entire like conversation transcript so far. And then it says there's a notion of like some true goal. And then for the blank of the true goal, we basically substitute in like each of the goals that we have. And so we do like X iterations over like the X goals that you have, and you substitute in like each goal. And also in the prompt, like the last sentence is basically like the human utterance at this round. So basically what we can do is we can measure like we're basically measuring the probability of the human utterance being produced given the whole entire transcript and like the goal set, like the true goal being like one of the goals. And so you can basically splice in to the logics that compose the human utterance and basically use that and then normalize that over like all the, if you do that for all the goals. So I think this is probably closer to what you're thinking about, yeah.
I mean, the one way would be to just like literally get the token likelihood
Yeah.
of the answers.
Yeah.
Right, the different goals, and then normalize it by like say sampling the base.
Yeah, but the problem with that is like so the reason why we had to do like
I think
basically
you'll have to normalize the length. I think that's what you're doing here by making sure that you take the likelihood of the
Yeah.
of the human utterance.
Yeah.
With restriction.
if you look at the like if basically doing it the logic way would be closer to like a true Bayesian update. The reason why like you like actually the equation should be like probability of goal given utterance,
Yeah.
but like we're doing the like in that method we did the opposite, which is like we're saying the proxy is the key of the utterance given the goal. Like we basically reversed it, and the reason why is because like you typically like to do a full true Bayesian update, you would have to know like every single possible goal you could have.
Yeah.
To do the true like probability of goal given utterance, but that's not actually possible because there's like a million ways to say like the same goal.
Yeah,
And
but
so
I think that's
basically-
why like the question that Hao asked, right? Like you could sort of take like some kind of Monte Carlo
Yeah,
observation, which I suppose you were doing because you're sampling only a certain number of pairs, right?
but yeah. But so we did do the logits method, and basically what we found is this is why we actually kind of like didn't have it in this version of the paper, is because like we normalized over everything, and basically we saw like the numbers that popped out for the distribution were either super close to 0 or super close to 1. It was just like 0.00 or like, so it was like not actually very informative for the sake of the distribution. It was actually good for ranking in terms of like if you just did this argmax, like if you just took the argmax, it was correct. Like it would give you a pretty good like that it passed all of these like tests for being pretty high up. But the problem is like for the sake of using it for the distribution, it was not very informative.
How did you set the temperature for that experiment?
So for that experiment, another limitation was like you had to use open weight. You had to use like open sourced. So we just like kept the like temperature like exactly the same to make it reproducible. I'm just like yeah. It was also very slow, and it was also it was just this is why we kind of like didn't actually like report the number. Like we moved on from using that method, but yeah. So cool. Moving on to our actual experiments. So we test in 3 different domains, and so we have they're all text based. We have a grocery shopping agent where we have a grocery shopping agent, and then we have a robotic like object rearrangement kind of task, and then we have also coding tasks. And so I mentioned earlier that we basically handcraft like 10 personas for every single domain, and they all kind of look something like this, which is like super complicated for lines over various things. So for the grocery domain, we have 10 personas. They're all over current ingredients that you might want. We have 5 that are over like various different cakes. So they're all like different allergies, different like textures, like flavors, etc. There's also 5 more general like dinner ingredient type of things, and those are more vague, less specific. There's some implementation details where like for the inventory search, like we had to do like some sort of like embedding similarity on top of LLM filters based on search queries, and the search queries are also dependent on the goal distributions then. And then we also have to evaluate on the final outcome, which is some notion of like how well does the grocery cart align with your preferences. For the robot domain, there is like an actual robot that's like going around and playing with these like various different objects. We also, for now, because the scope of this work is only on the text part, so we actually rely entirely on the metadata of all the actions done, like nothing from the visuals for now. We have 10 personas over like different object preferences. So it's like grab me a breakfast sandwich, like that sort of stuff, or like object rearrangement. In AI2 Thor, it's actually kind of interesting. Like a lot of the low level actions are completely abstracted out. You're only worrying about like, grabbing objects, and there's only like a limited set of actions that are allowable per object. And so basically we have to do some extra scaffolding here where it's like the list of possible actions are also dynamic, because like depending on what object you're holding, there's only like certain actions that are available to it. And this basically like which objects are relevant are also informed by the goal distribution. And then I think probably to most people here, the coding domain might be like most interesting or probably most applicable, I guess. But so we have 2 versions of the coding domain. We have one that I titled just like coding, and that's handcrafted 10 personas over various coding and function preferences. So this might be like, I want more comments, like that sort of stuff. There's also a stateful SWE benchmark that exists publicly out there. And what the stateful SWE benchmark looks like is kind of like if you take SWE-bench and then you add on, or they've added on like curated coding preferences and human interaction preferences. And so I took 5 problems from there. And I also relied on a coding agent aider to help like actually propose like the code edits. So we have to, going back to reward, so we don't actually have a reward function because it's actually really hard to obviously like come up with, you know, a good reward function to be like, hey, this card is exactly what I wanted. So what we do is we have to rely on like LLM rubrics. And so we measure a couple of different metrics here. So one is conversation score. And this is kind of like,
Can I ask why is it hard? I mean, isn't that just a list?
So because we also make it like we test in a bunch of different domains, so it's like pretty hard to like come up with a shared like reward function for every, like it'll have to be like hand designed to your different domains.
But I mean, at least the evaluation for specific things can be like what exactly makes
I mean, like the thing that makes it hard is because like we curated the personas without having a notion of a ground truth card. Because like if you think about it, like,
you have to assume that there exists a ground truth list, right? Otherwise, like there is no goal.
so we don't have a ground truth list.
Um,
And the reason for this is because like if you think like there's a bunch of cards that can satisfy your preferences, right? If you said I wanted something sour, there's like 10 different cards that could probably satisfy this.
Okay.
So like it's actually really hard to make a reward function for something that like to look for a card that's like that's sour. The best way would be to actually give it to an LLM rubric and be like, hey, this is satisfy my preferences of it being sour, for example.
Yes.
So yeah, it's just justification for like we have to resort to like some sort of rubric and doing LLM judgments to like basically evaluate all our experiments. And there's no like you can't really apply classical POM-DP solvers to this type of test, for example. So yeah, we evaluate on a bunch of different scores. So one is conversation score. So we want to make sure because like the topic of your dialogue and a lot of your queries are actually also based on the goal distributions. And so we also want to evaluate to make sure that the conversations are on track. They're actually useful for preference elicitation. And it doesn't like diverge from your preferences too much. We also look at the action score. So are the actions taken like line? Do they make sense with what you want to do? There is a task performance score, and that just like evaluates the final output. So for the grocery domain, it's just the final cart. For the robot domain, it's your action list that's been done, like all the actions that have been taken in the environment, and your coding environment is just like the final code that's been output. And then finally, we also do like an interpretability score, which is like.
Sorry. So, I mean, at least for the supermarket case,
Yes.
if you define a supermarket by the inventory, right, as the abstraction, then there exists a ground truth, right?
So no, because the agent can choose from the whole entire inventory that's in this.
Sure, and they map to some list of sour things, list of. I mean, if you're creating the environment, you can totally control this.
I mean, we could, but like because the way we deliberately like chose preferences that are very complex, then that makes evaluation hard.
Maybe if you could explain a bit more on this. So let's go back to the lambda cake example.
Yes.
So let's say your agent came up with a card
Yes.
to build that, but
Yes.
it did the same thing of just picking like the fancy items and not anything about the cake.
Yes.
But since you're relying on LLM as a judge to evaluate that card, wouldn't that say this looks good?
So I think those are evaluation.
Like because you're not specifying like any particular criteria to your LLM as a judge to say that.
We are. So actually, like in our criteria, we do have like, these are example of things that should be in the card.
But I mean, then you can't, okay, fair enough, right?
Yes.
But then that same list can also be used to populate the environment from which you pick.
But
And
like the
then there's a
list
one-to-one mapping.
doesn't, the list is not like. Because like in your inventory, you could have, like, there's like 5 different types of lemons, right? Do I care if they're organic or?
No, they all map to the same ground truth.
Yes.
And so,
So this is why we have a rubric that's like, any of these similar things, as long as they're in there.
no, but then
right.
why rely on an LLM as judge in that case? If you have a mapping, then it's a deterministic score. Right? Like if you're saying here are 5 lemons, great. You know, 5 lemons get the same score.
Preferences is like one lemon. Because like we have 5 preferences that are like, I want
I
like,
mean, so like it's all I'm trying to say is that yes, it's a complicated environment to set up. It's not an impossible one, right? Like yes, there's many things that can replace, like sort of a certain item, but you can construct such an
yeah,
it's just a list. Like many to one mapping or many to many mappings. But it's a perfectly describable deterministic environment to construct.
yeah, it is. Yes. But then you could have like 20 different cards that would work.
Sure,
Yeah.
but I mean,
But, like,
the score is trustworthy, right? I think the
Yes.
point that Shiv is mentioning is the same issue I have is that, like, why do you trust another LLM, not the one that picked things,
We,
right? What extra information is available to this LLM? And if there is extra information closer to the ground truth, and then it is possible to construct an environment where this can be deterministically constructed.
Yeah, maybe in your setup, let's say if GPT 4.1 mini or whatever is the shopper and the judge,
yes.
what additional like privilege information do you give to the judge in order to evaluate?
So the judge has like better, like for each like LM prompt, like it has well, it depends on so we have to hand make some of these rubrics. So like for example, for the grocery domain, like a lot of them are provided like, hey, like for this preference, for this specific person's preference, you should have items that like have this kind of attribute. So we give it more like more detailed information about like.
And
attributes about
that makes
it.
perfect sense. I guess like my
Yeah.
issue with that is that you have enough information there to make it a deterministic match problem, rather than relying on LLM as judge, because one issue with LLM judges, they're also not calibrated. So you then have to factor how badly this is doing.
Yeah.
Right. Whereas you were giving it enough privileged information that you could just convert it into an actual score.
Sure.
Right.
We could. We didn't do that.
Yeah.
I also okay, I'll show you. We also like sanity check some of the evaluations. So I'll show you the results from that. But yeah, and the last score we do is interpretability. So this is basically like for if you have the goal descriptions, like how reasonable are the goals that are produced? Like are they relevant? And also like can you trace the actions that are taken to these goals? Cool. And so yeah, we got a lot of similar worries about, like LLM evaluations, like, oh my God. So what we do is at the very beginning of this experiment, we actually compared to human readers. So we give the same rubric to an LLM and to a human, and we say, rate them. And from our initial, these are just proxy experiments, so obviously they're not the exact same experiments we had at the very end, but we can basically kind of like the judgments that we got are basically there is like some discrepancy as in like there's like a 10% gap, like for example, between human raters and like LLM raters, for example, but the ranking of the methods are correct. Like they match up.
Did you calculate the correlation score?
Yes. So this is just I have Pearson correlation, but this is just like based on the means. And the grocery domain they matched up like 99%, and then for the robot domain it was like 85%. At the time we only had 2 domains. Those were the only ones we tested. So yeah, the correlation is pretty high. Cool. And then for our main experiments, we do compare to some ablation or like some baselines. So we have full context baseline, and that is if you were to give like the full context to the to like an LLM every single time. And for our baseline, we use like at the time, or when we read the experiments, the best model was like GPT 5.4 mini on higher reasoning. We also compared to summary context, and that is if you gave a summary of everything that you said to an LLM and asked it to plan. And again, that's the same, we use the same model for that. And then we have our two variations, which is good, one with prompt, and so that's just like LLM being prompted, like what is the most likely, and then just take the action based on that. And then we also have good with probability, and that's the binary pairwise comparison method. Cool. And then yeah, we tried various different trios, so it's gonna be like kind of a messy graph, but basically in our method for each module, you can actually just have a different like model doing that module. And so this probably goes back to your point about like costs. So you can, like, depending on what combination you do, you can kind of like play around with your like cost tolerance for different models and stuff like that, because you don't necessarily like need a super good like you don't need to spend so much cost on your action planner if your goal performance like abstracts some of the like saves you some of the cost there. So things like that. But yeah, this is kind of hard to see, so I'm going to circle things. But the blue and orange are the baselines. Everything else is stuff from our method. And you can kind of see like the stuff I highlighted in pink. It's kind of either competitive or does better than the blue and orange. And you can see kind of like this is average round per like cost. And so yeah, our method at times is slightly higher for cost, but I would agree to take that cost if the performance is higher. So, but that's obviously up to you and your risk tolerance. And you can obviously play with the different models. And so I do show like a scattering of like if you have different models, and you can have higher performance, but sometimes like the cost is super high, and maybe that's like something you don't really want. But yeah, you can kind of see like over the different domains, like the different experiments and personas that we run. These are kind of the averages over 3 different trials for each persona. Each of them are scored twice. And so that's why those are the error bars for like standard variation or standard deviation like across the mean for all these experiments.
So the ones that you circle, what do they mean?
They're basically the ones that I pointed out for like
Are they on the,
decent cost, higher performance, or comparative.
are they Pareto optimal, or they're just your best choice? Like, you know.
Like I just took a look, and yeah,
Okay.
yeah. I mean, you could try more models. We had finite budget and finite compute, so we just tried a bunch of like the GPT different models. I'm only on GPT 5.4 and 5, the nanos, some of the different like reasoning levels. We didn't try all of them because that's a lot. But these are at least like a some scattering of some of them.
And so what are the different y-axes? They say car to score.
So here, this is just for like the task performance score. So this is for the grocery, it's like the cart, the code, the action list. And yeah, so basically from here you can see like you can get competitive or better performance from goal tracking at a slightly higher cost.
For the coding graph, do you have like the orange? I don't think I see on that.
So they're on top of each other.
Oh, okay.
Yeah.
Which one, sorry?
So the coding on the left,
Yeah.
like the blue, what you see is the blue, the orange is like right underneath it. It's like slightly like sticking out.
Okay.
So it seems like in the coding case, you see a significant improvement with your method, right? Compared to the baseline. Like there is an infinite scaling happening where if you put more tokens to generate better and better answers.
Mhm.
So you're saying that like I'm just trying to parse the code ones because they're very interesting. So it seems like that the intent or like goal tracking is in the grocery case, probably it's not a very hard challenge, but when it comes to like very sort of technical things that have a lot of nuance, that's where you start seeing benefit
Yes.
of sampling multiple
Yes.
load hypotheses and then ranking them. in a
Yes,
specific-
there is that. There's also other, yeah, there's also other possible reasons to why the gaps are quite different. So one is, for the robot and the coding domains, the gap between all the scores in general are bigger. Like you can see larger discrepancies, and this is because like also by the nature of like, for example, in the robot domain, like if you take a wrong action, it's like very clear it's a wrong action. Versus like in coding as well, like if you make a mistake, it's like clear, like half the code might be gone or something like that. Versus like in the grocery domain, like if you forget like an item, like the score difference is actually like quite low, for example. Or like if you care about like how do you like it's very hard in the grocery domain to really like categorize the difference between like if you left something organic out versus like if something is organic, or if you have like a bag of lemons versus a single lemon. It's kind of like so that's why like for the grocery domain, like things are just like quite closely clustered together. Like the errors are less like it's just like harder to see the errors between different carts, for example, if they're super close. Versus like, yeah, it's just like easier to like see, like look at the actions for a robot or coding and see like, oh yeah, that's definitely an error. I'm gonna like dock you up 10%.
Also, these numbers are not purely accuracy. These numbers are the cumulative LLM as judge
Yes.
score as okay.
Yeah.
Okay.
So for the coding domain, you measure whether it's aligned to the user preference, let's say like,
Yeah, for this it's just like it's looking at the code and it's like, is this aligned?
okay, and it's also testing the functionality of the code, right?
Yeah.
So you're actually running the code.
Oh, so I'm okay, so that is actually a good point. So I did not run the functionality.
Okay.
And the reason for this is it's capped at some number of max rounds. So most like for a lot of the cases, the code's not complete.
Mm.
So we will take whatever is at the final round and evaluate that. And for code, it's like I didn't run the functionality test because half the time it's just like midway there, so I'll not do well. The other thing is like there's a lot of for a lot of the preferences. For example, if you had like I want more comments or something like that, if you run the functionality, like that doesn't check for if your preferences are met. The same with the stateful suite like code bench, like a lot of the preferences that they inserted actually have nothing to do with the code. Like it won't show in the output the code. So that's why like running a functionality test, like you could run them, but they're not like actually useful for determining whether they align with your preferences.
In that case, wouldn't it be similar to the grocery domain where it'll be hard to kind of like evaluate between two pieces of code, one that has like a little bit more comments than the other one?
Yeah.
They'll still be like relatively closer to each other, right? Like how could you explain the bigger delta you get?
I mean, it's just like for code, I think it's like easier to determine if one has something or one doesn't. Versus like for the grocery domain, you have your state space in objects is a lot bigger. And so like you have a lot more similarity between like if you grab like different or like there's no difference between grabbing a single lemon versus like a bag of lemons in the grocery domain.
Right.
And that is different from the coding domain where if you had comments versus not enough comments, like I think that's like a judgment that is like better able to make. Like I think that's a clear judgment, like if you asked it like, does this code have more comments? It's like a really like a yes or no.
But if you take away accuracy of the execution, then isn't that like to me the coding domain made a lot of the reason I was very interested in this is because it's a constraint optimization problem. The constraint is that the code should always work and finish the benchmark problem. But should also respect all the constraints I put. Right? So I'm not sure how to interpret this number because you're saying, hey, execution, I don't care as long as you can just agree to the style and particular constraints I'm putting without achieving the goal. Because it's an easier problem for me to then say, yeah, I can do all the commits and everything in the right order if it doesn't matter whether the code works or not.
Yeah, like in our LLM, like in our judgments, we also like it does like we do ask it to look at functionality, so it's not like because like some of our preferences are over functionality.
Right.
It's just like yeah, we didn't actually run the functionality tests. Yeah.
Yeah, maybe for a tangible, like more tangible example, I guess though, like if you look at the current coding agent, most of them, they could get there by like solving the task or like passing the unit test.
Mhm.
But the main difference between, well, or at least from the ones I've observed with like Flood Code or Codex and all of the stuff is, the patches they make or like the changes they make, they differ in quality.
Mhm.
Like one might just, and like nuke the whole functionality and rewrite it
Mhm.
in like a more complex way or like a downward
Mhm.
way. And one would make more like surgical changes.
Yeah.
And still sort of get the like correct execution.
Yeah.
Like, yeah.
Yeah.
So I guess like what she was saying, which is exactly what I was trying to get to, is that like if we look at all the like I mean two things. One, how many patches were actually correct? And then of those correct patches, how many actually adhere to the constraints?
Mhm.
Right? Because that's typically a metric I would care about a lot, right?
Mhm.
Like, because if you're writing if you're writing functional code but it's garbage, I can't read it, then it's also kind of like I would give almost close to a zero.
Mhm.
So I think like your overall design is justified, but the fact that I don't know whether it will work or not
Mhm.
is kind of where this is getting a little bit, like slightly less useful.
Mhm.
That's it.
Cool. And yeah, like digging deeper into why like basically like goal inferences could be helpful here. Or like might explain some of the differences between like why we do so well in certain aspects is like so in our goal management module, our prompt is not only like when we ask it to come up with new goals, we're not asking it to just come up with a summarization of basically what you said. We asked it to also like the prompt is actually much more complicated than this. I don't show the whole prompt, but we also ask it to basically like come up with like goals that it thinks you might want. So those are goals that you might not have said, but you might have like for example, like you don't have to actually say that you want a cake. But like if you've been saying like things that are leading to you might wanting a cake, then your goal, one of the goal propositions that will occur is like it will actually propose like baking a cake as an option. So it's not like just inherently a summarization of what you might want. And so that's probably why like there is a discrepancy, like there is a difference between our method and like the summary context baseline, for example, because that just like works in a summary. The other thing why we think that there's a lot of a better performance is because the way we like generate these conversations is like the dialogue topic, as I mentioned before, is based on your goal distributions. And so basically, looking at the conversation scores, we can see that the conversations that they're having are better, or at least like in most cases actually better. And so that means that your conversations are actually are actually working towards like eliciting more of the human preference that is relevant. Versus like if you didn't really have good goal tracking, then that means like your conversations might kind of derail at the end. And might not actually be useful to discovering like what more of your other preferences are. So we can kind of see this like there's a bunch of highlighted, circled in pink that like the conversation scores are higher. And finally, yeah, looking at interpretability scores, so this is just kind of a sanity check of like, if you have like a no goals or a summary context baseline, like they don't really have a notion of goals. So basically it's harder to track like where the action selection is coming from, given the whole entire context of your conversation versus our two methods where you actually have goal tracking, then you can actually like trace back where the goals are coming from, or where the actions are coming from the goals, and also like if the goals are actually reasonable. So yeah, in conclusion, we propose like a new framework, open universe assistance games. We come up with an LLM method to kind of put this in practice. And talking about future work and related work. So as Hal mentioned earlier, I do have a human robotic interaction background. And so we really do want to put this into an actual like robot or something that actually like takes actions in the physical world. And so one thing that we were looking at is so far this entire work that I explained has entirely been in text. But in order to reason about embodied space, you really need vision. And so I have mentored a Europe project, and this was a workshop paper at CVPR, where we were looking at basically how well are VLMs, like how well do they do at reasoning about these more complex, like dynamic human preferences. And so in that piece of work, we basically curated like a little data set that we made with a little bit more complicated human preferences. And so an example of this would be like, hey, if you take an image of a fridge, for example, and you're like, I like to order stuff in my fridge by color. And then you give it like a new object, and let's say like, you have a banana or something, and you're like, hey, where should I put this like in my fridge? So things like this where we realized that like current existing data sets are really not good at like, they don't have a lot of cluttered environments where we can do this kind of thing, or they just like have very simple preferences where you can actually reason about it without looking at the image at all. Like those are the main problems with the current set of benchmarks. So we kind of like created a little data set of our own, where we made like varying different difficulty of preferences to some of them like don't really need the like visual data sets, for example, or like anything from the image versus like preferences that really do need stuff from the image. And we basically evaluated a bunch of like open source VLMs and some closed source like GPT like VLMs, and we were able to show that while there is a gap between the performance of like open sourced versus like closed source VLMs, some of the recent like open source VLMs actually do also really do well on this data set, versus like some of the older closed source like are quite lacking in this. But this is basically a sanity check to see like, VLMs are at least decent enough to kind of reason about these types of complicated dynamic human preferences. And so basically, we can now shove this whole pipeline that we had into maybe a VLM, and then we can basically do the similar inference in a more embodied like visual way too. And so our next task would actually be towards like putting this into an actual robot and having it kind of do active learning in a visual environment and be able to reason about hopefully both textual utterances from a human and from the visual like observations that it gets. There's also other possible expansions that we've been looking at. So far, like a lot of this interaction, this is a very interactive like human AI work. And so so far we've been assuming that the human has like a lot of just like been giving most of the information and the agent is just querying. Of course, you can get like a more equal like bidirectional information gain. You can especially think about this in terms of like household environments where like the robot can give you observations, like you can give it observations, and having kind of a more equal like amount to work off of. There are interesting questions here about like, what is like the minimum amount of information you need to be able to give the task like that, or to be able to do the task, for example. Like those are interesting questions that arise. There's also interesting like cog-sci or like human social interaction questions that you can actually raise up, such as like deception. For example, like also just like you can have really cool questions where like you might push the human to shift their preferences. And so it'd be interesting to dive into work to see like, how much of your preference like can shift depending on like the nature of these queries, for example. And one last thing we're also in the middle of working on is, we recognize that a lot of these evaluations are quite there's a lot of pushback on our evaluations because of the LLM nature of them. So we've been also looking at developing a benchmark for specifically like the goal annotation part, where we are working on getting we have chat transcripts and we're getting people to like annotate with like possible goals, likely goals, and so we can do like cool cool benchmarking against an actual like legitimate benchmark. So cool. Thanks, Aaron.
Thank you.
I think we're running out of time. Maybe we can bring the call first.
Yeah.
Yeah, thank you so much for everyone who joined remotely. Yeah, maybe cheaper also and